right, we've finished up our univariate analysis. Let's move on and get started with our bivariate analyses. So the first thing to know is we've got three different possible combinations of bivariate analyses we can perform. First, we can compare numeric to numeric values. Second, we can compare a categorical attribute to numeric. And then third, categorical to categorical. So let's go ahead and start with what we're all probably most familiar with and comfortable with, and that would be numeric to numeric data. So the way to do that is, and we'll start in Tableau as you can see here, is we'll just create a scatter plot. So I'm going to create a new sheet, and we'll bring in age as my columns, and then charges as my rows. So if we know what the target variable or the label attribute is going to be, then we're just going to do our bivariate analyses against that label attribute. Okay, so you see I get my single dot here, so I'm going to disaggregate this. And right away, we see we've got something interesting going on here. I'm going to spread this out a little bit. So you can see we've got what looks like three pretty distinct patterns going on there. We've got a densely populated lower band that seems to have a slight curve to it, trending upward. And then we have a mid-range band there, and then an upper range band there. So a large group that in all three bands, you can see, seem to require more medical services provided by our insurance company as they get older. But we've got this big band where it looks like they probably just, they're reasonably healthy. They don't have to go in to the emergency room or get any major treatments very often. Then we have this middle band that may have a little bit of work that needs to be done or have some kind of special diagnoses done periodically. And then we've got the group up here, including a few way up there, that have probably major issues and major costs, okay? But it seems to span those three bands, not particularly any age group. So this is kind of an interesting distribution. But we'll get into that. For now, we just want to determine what the trend is, okay? So we're going to go into Analytics and create a trend line. So I'm going to just click on that and drag it out here. And you can see the first option is a linear trend, okay? So I'll drop it on there, and you can see I get a trend line. And as I hover over it, I can see here is the regression equation that creates this line. We've got an R-squared of 0.089, and we've got a p-value of less than 0.01, so definitely significant. Now, I can also create a description of the trend line and see what's going on here, and I could see a little bit more of my statistical information on that trend line. And I can also have Tableau offer up a description of the trend model itself. So I've got a fair amount of statistical output I can look at and work my way through here. But for the most part, I'm mostly just interested in those, the regression equation, the R-squared, and the p-value. All right, just for, out of interest, I might come in here and bring in smoker as a color. And you can see I end up getting two trend lines, and you can see most of the lower value items. There's a much lower value of charges for the regression line for non-smokers versus smokers. And I'll take that back out now. And then I could do the same thing with sex to see if that shows anything much closer there, not as much difference, okay? Region. All right, yeah, a little variation there, a lot of similarity. So you can see there's a lot of additional analysis we'll perform and can perform, but for now, we're just really trying to determine what our or what our scatter diagram looks like and what's the best trend line. So here's a linear trend line with an R squared of 0.089. Now, you may have noticed when I dragged trend line out here, it gave me a number of different choices. So I can actually do a logarithmic, exponential, polynomial, or power. So let's start with logarithmic. And you can see what that does is it uses the natural log to calculate the trend line. And you can see that gives us an upward slope that tends to level out. R squared of 0.084, I've got my regression equation based on the natural log of age, and then a p-value of 0.01. So all of these are significant, but the straight line was a much better fit, or at least a slightly better fit based on the R squared. Trend line, let's go to exponential now and see what we can do. And so this does the opposite. It basically creates an exponent of the natural value e times age. And that takes our R squared way up to 0.2786. So that's much higher. And you can see that tells me I may want to use that exponential value of age in any modeling efforts that I want to do that use a regression approach. All right, let's do it again with polynomial. And you can see polynomial, since I'm now using squares, gives me a line with multiple inflection points. So that increases my, well, actually that doesn't do a whole lot for my R squared. So that's 0.09, a little bit better than what we had with the first couple, but not nearly as good as with the exponential. But you can also see it makes our equation a little more complex because we now have to square age and use that plus the original value of age. And actually in this case, it uses a cubed value of age as well. So there are coefficients for all three of those and our intercept. Finally, I can use power. So this one gives me what looks like a pretty straight line, but in actuality, there's a slight curve to it. And this one also gives me a pretty strong R squared. I may have to go back and double check, but I believe this one might even be a little bit higher than what we had for the exponent. So this one allows me to raise age to whatever power I want. I don't have to square it. I don't have to cube it. So in this case, you can see it offers me, and it calculates the best fit for that trend line this way. The age raised to the power of 1.25954. All right, so with this, I can start recording these values for my model, and then I can add these scatter plots to my documentation. So I'll go ahead and I've done that for age. So we'll say age or scatter age charges. All right, so the next one I'll do scatter BMI charges. And these will go through a lot quicker. So BMI charges, disaggregate, got my scatter plot. Looks, kind of random there. So we definitely have a lot more variety going on here, more variability. But let's go ahead and create a trend line anyway and see what we get. Start with linear, and yeah, there's definitely a slope, 0.39 R squared, still significant from a P standpoint. All right, let's try the other options for our trend line. Logarithmic, 0.039. Exponential, 0.017. So exponential doesn't help us much here. Polynomial. All right, so you can see we've got a more dramatic curve with this one, and that raises us up to an R squared of 0.041. then power 0.01. So polynomial is the best by a long shot here. And it used my cubes, squares, and BMI, the original value. And we've got 0.041. So that's my best. All right, so that leaves us with one more to go. And we'll do scatter of children to charges. All right, so children are my columns. Charges are my rows. Disaggregate. All right, because children is a discrete variable, I end up with a bunch of columns of data points here. And you can see I've got a pretty good distribution across every number, but it looks like there may be a bit of a trend there for us to look at. Let's see what we find. Trend line, linear. All right, yeah, so there's definitely a slight upward slope. Real small r squared, 0.004. P-value, we have our highest p-value so far, so 0.01. So it's less significant. So let's try the other trend lines and see if those give us anything. Logarithmic, yeah, 0.003. Exponential, 0.02. So a little bit better. Polynomial, at least we're up in the hundredths. R squared of 0.0118. And then power 0.014. So in this case, the exponential with 0.026, I think, gives us the best. So that's not a great R squared, but in many cases, depending on what we find, sometimes, you know, a little tiny R squared can still be meaningful for us, especially if we didn't know it before. All right, now let's flip over to Excel and see how we can do basically the same thing in Excel. So Excel gives me the ability to create scatter plots as well. I'll just highlight my columns here, ages and charges, and then I'll tell Excel I want to insert charts, scatter, and I've got a scatter here. All right, so it's pretty just as straightforward as it was in Tableau. Easy to get one built, and I can size it however I want. And then I have the ability to add a trend line here. Okay, so I can see that same trend line I had before. And then if I click over to the right of trend line, I can say, well, give me a linear, exponential, and then if I actually click on more options, I get a little formatting pane over here where I can choose what kind of trend line I want. So I could choose exponential here. And actually, one thing I want to do is I want to display the equation on my chart and also display the R squared value on the chart. So I'll bring this out just a little bit so we can read all of this. All right, so you'll see what it does is it kind of sticks it in here. It's hard to read. So I'm going to drag it up over here into the corner and make it a little bit bigger. All right. All right, so here I've got an R squared of 0.09. And now I want to go back to my trend line. Let's make that linear again. R squared 0.0894, and you can see my linear equation. Logarithmic 0.0841. Polynomial. Now Excel gives me the ability to make my polynomial to whatever order I want, all the way up to 6. So I change that to order of 3, and now I get cubes in there, order of 4, order of 5. And you can see my R squared improves slightly every time I increase that. Well, it doesn't look to me like we're going to get to the point where, you know, where it's going to be that great. So 0.0925, and then we go back down to 2, 0.0906. Not enough of a difference for the added complexity. Okay, so now power. 0.0901, and then I've got a moving average one that I can use, which is not real useful for us. It's more, that's going to be better for your financial analysis, like analyzing a stock price against some kind of a moving average. All right, so polynomial gives me my best R squared here at 0.0913, or 0.091 at cubed. We'll just leave it at the level that Tableau had. All right, so now we'll go to BMI and charges and insert a scatter diagram there. And we'll drag that down here below. And then we'll do the same thing. We'll create a trend line, show trend line. More options. So now I can ask it, first I want to display my equation and my R squared. Drag those up. Drag those up where I can see them a little bit better, and then make them bigger. And then I can go back to my trend line and start my formatting. Okay, so I've got an R squared of 0.039, exponential gives me 0.038, logarithmic 0.0397, polynomial 0.0401, increase the power, and it seems to help a little bit. If we leave it at 3.0414, power 0.0397. So polynomials are again our best bet for this Excel version of the Scatterplot. And then I can go down and do the same thing again with children. So children, charges, insert, charts, scatter. And that gives us that chart we had that was stacked by age. All right, show my trend line. And then I can click on display equation R squared. Increase the size. And then go back to my line and start formatting. All right, so right now I've got 0.0046, 0.0038. Okay, the logarithmic won't work with zero values. Polynomial. 0.0085. Increasing it to order of 3 actually helps quite a bit here. Helps a pretty good amount again, but we're still at pretty low R squareds there. I'll put it back to 0.3 or power of 3. And then power, again, looks like one that doesn't work well with zeros. Okay. All right. So now let's calculate the Pearson's correlation for each of these three pairs. And we can do that in Excel. Let's just say correlation, Pearson's correlation. We can do that just by using the correlation function. So correlation. And then I would like to calculate the correlation between age and charges. Okay. And I can see that's 0.299. All right, let's do the same thing down here for body mass. And again, I'll start with body mass. And I've got a correlation of 0.1983. Okay. Try it again. Down here for number of children equals correlation. Number of children. Charges. And I've got 0.067998. So you might recall from your reading in the reading module that anything below 0.1 we consider not really an effect worthy of our interest. So it doesn't look like the number of children is really a big factor in medical charges. So now we look at the other two. So we've got body mass with an effect of 0.19. That fits right in the middle of the range we would consider a small effect. Okay. And then up here with age, we're right at 0.299, so almost 0.3. So really that's kind of on the threshold between the small effect and the medium effect, what we would consider a medium effect. So remember, anything between 0.1 and 0.29 we would consider a small effect. Between 0.3 and 0.49 we consider a medium effect, certainly worthy of interest. And then anything above 0.5 we're going to consider a large effect. And if it's way too large, then we may want to consider, is this really, are we really looking at two different things here? All right, so we've done our bivariate analyses for our numeric versus numerics. Let's get back to some more work.